Okay, so hello everyone. Welcome to this talk about the Chisel tooling, which is what we are currently using to use a bottom-up build strategy to build minimal and secure Ubuntu containers. And let's dive into that. So, just a quick survey. How many of you have great experiences in containers? Please raise your hand. Very nice. So just a little intro to the containers regarding like if anyone has feel a bit foreign about it. So for containers, what we do for a normal system, we have our infrastructure, which can be your server, your cluster, or even your laptop. And based on that, we have our operating system. In this case, I'm using Ubuntu. And after that, we have in the application level is a container engine. Normally you have Docker, but if you're from Red Hat, you can also be using the Podman and also many other container engines. And based on that, we have containers. Every container is being spawned from a container image. And in that image, usually you have your application and also the binaries and the libraries that is required to run the application. In our world, we majorly have 4 types of different containers. The first is the base images, like operating systems, for example, Ubuntu or the hardened Ubuntu. And second type is the tools, for example, like SDKs, just like .NET SDK that we are shipping. And third type is runtime images, like the .NET runtime, the Java runtime environment, and also Python. And lastly, is the applications like Nginx, Apache 2, MySQL, and Prometheus. According to a survey or a prediction that by 2029, 95 of the applications running in the global organizations will be containerized in their as a production, and 35% of all enterprise applications will be run in containers by 2029. And by 2028, 80% of the software running at physical edges will also be containerized. Then what are the important criteria of building a good container image? Also, according to a survey, that the first among all is the security. And also stability, size, compliance, and provenance. They are the most outstanding features or the criteria that we would like to have from a good container. Then this imposes enterprise challenges. The first one is about maintaining or patching. The top 10 images on Docker Hub are suffering from vulnerabilities naturally. And it usually takes average around 21 days to fix them. And although using the container technology, they are easy to learn, but not necessarily easy to master. So everyone can create their own application container, but only few of them can make it minimal, secure, well organized, and maintainable. There are also complexities in management, say, because the Docker file itself has its open nature, so it leads to some inconsistencies between the images and the solutions. And lastly is regarding security standards and compliances. Since they are increasing industrial requirements and also from the government regulations that we have to have our container images comply to those to some specific security policies. And let's see how we build a standard runtime image. So we basically follow the pattern. It's like from Ubuntu, whatever version, and we run apt update and apt install, which install all the necessary packages that you would like to have in your final image. And finally, we set our entry point. And on the right side is the example that how we build a Python 3.11 image based on Ubuntu 22.04. Basically, we start from Ubuntu 22.04 as our base image, which is a full Ubuntu container image. Then we set some group ID and UID to be non-root, so we don't give excessive permissions to the container image. Then with the run command, we will update our package manager and install the Python 3.11 packages, which also handles the dependencies automatically regarding that package. And after that, we're doing a lot of cleanups for the image, because the package manager, both apt and dpkg, they will generate amount of logs and caches. And finally, in this run, we will add the group and user to our system. Lastly, we define the user to be running is daemon and the entry point to be Python 3.11. However, building with such pattern, we will still have a lot of residue of additional utilities from the Ubuntu distribution itself. For example, like those interactive terminal tools like AWK, grep, ls. If you're only running a Ubuntu image, you won't need those terminal utilities in the distro. And we can see the image size is going to be around 43 megabytes. These images, this size is being counted as the disk size of the OCI archive. Then we'll have the concept. If we are not using those utilities from the distribution, is it possible for us to run or to build a distroless runtime image? Yes, it's possible. Take a look for the first idea. For the first concept, it inherits from what we are having in the Docker file. So we can use the pattern of multi-stage building. So in the very first stage, we make it as the build or the builder from 22.04. And we install all the packages and their dependencies, just as before. Then in the second stage, we start from a scratch image, say an empty image. And we want to copy all things that we require from the first builder image to the final target image, which is starting from scratch. But wait, here's the problem. What are the files and their dependencies required for us to copy from the first one to the target one? That's a bit complicated, because for Python, especially the C Python, you will need a lot of dependencies, even the libc. Now, how to determine them if we are going through this up-bottom fashion is really hard. Well, Google proposed a very nice solution. They use Bazel to build their distroless images, for example, like Python 3.11. So in their building recipe, they write the packages that is going to be included into the image, and also a bit of other settings. And their resulting image size is just around 20 megabytes. However, since many organizations, they do not use Bazel from the beginning. So if we introduce Bazel, then we're definitely going to introduce some technical debt. And also, this building recipe is around 127 lines of code long. It's a bit lengthy. How can we deal with that? In Canonical, we have such 3 tools as our tool chain to build container images. The first one is Rawcraft. It is to create secure, organized images. And firstly, it's a declarative build recipe instead of the Docker file, which is imperative. And we have the very familiar craft syntax, which is based on YAML. And lastly, it supports distroless natively. The second tool is Chisel. So with Chisel, we can crave out the slices from Debian packages. We can only retain the files that we require. And if we are building using Rawcraft, then calling into Chisel is just seamless. And with reduced files, we also reduce the attack surface, which results in a smaller image. With Chisel, what we are getting is just a slice of Ubuntu. The third tool is Pebble. Pebble is the service orchestration manager in the image. It also follows the declarative service definition and thus we have a predictable user experience. Also, it supports multi-process management, so it's natural that it serves as the init system for the containers. And with these three toolings, we build our artifacts, which is called ROC, or ROCs. It's the leading production-grade container images. So let's compare how we built the image from the full Ubuntu base. On the left-hand side is the example that I've already shown using Dockerfile. And on the right-hand side is how we build it with Rockcraft. Building with Dockerfile is a bit imperative. Well, it's indeed very intuitive for Linux terminal users that whatever file you put into it will be locked by the Docker build kit and put into the final image. However, it requires the user to have some deep distro expertise because you want to do the proper cleanup, you want to properly set the user, and the final resulting image size is around 43 megabytes. And on the right-hand side, you see the code that has the normal color. They are the really functional codes. And it's quite declarative. So you declare that your base is Ubuntu at 22.04, and which also defines the platform that you're building for. And for the run user, you can just simply put daemon, which has the same effect as on the left-hand side. With Rockcraft, we only put the declared components into the final image, say, like defined in parts. What we call is install Python, and here basically we just install two Debian packages. The first one is base files that makes the base file hierarchy of Ubuntu, and second one is Python 3.11, which we put into that. And with that, it requires less distro expertise, and the final resulting image size is around 42 megabytes. So when we're talking Rockcraft, we also want to talk about its support for distroless. How we can build distroless images with Rockcraft. Just changes in 2 lines of code, we will have it to be distroless. Instead of declaring the base to be Ubuntu 22.04, we declare the base to be bare, which is just the same as Scratch in Dockerfile. And we put a build base, which is actually letting the build happening in 22.04, and we pick all those necessary files into the final image. So as you can see, the stage packages keyword, all the files being listed there are going to be installed to the bare base. And with that, we will introduce no additional utilities from distribution. And we will have the entire Python package and all dependencies into the final image. And the size of the build image is just around 29 megabytes, although it's still bigger than the Google distro, but it's already smaller, way smaller than the normal image. However, with this difference in sizes, here comes the question: can we further remove those unused files, for example, the man pages, the documentations, the time zone files from the package? Yes, we can. Now we introduce our second tool, which is called Chisel. There's one further step to build a minimalistic image. As previously been stated, that the way we do with Dockerfile is more a top-down methodology. We firstly inflate the base image and then try to cherry-pick all the things to the target image to trim it down. But this fails when we are building the low-level runtime images. Instead, with Chisel, we can do the planned bottom-up way. So we start from scratch and build a file system from the packages that is available in Ubuntu archives. And we call this the modernization approach. This is because we don't have to let the user have very comprehensive understanding about the distribution or the very complex distroless build strategies and building recipes, while we still retain the original Ubuntu bits, which means for all the applications that is possible to run on a normal Ubuntu image, we can also have it run seamlessly in such kind of chiseled images. Let's take an example of how we chisel. Suppose for a Ubuntu distribution, we have 8 packages installed. However, for the application or for the runtime environment, we only require some subset of the packages. Say we would like to have some slices from package A, B, C, D, and E. And with Chisel, the resulting file system only consists of the file that is necessary. And Chisel is able to handle the dependencies automatically, recursively. Say for a slice that we require is the slice 3 from the Debian package A. And that slice is depending on the slices 1 and 4 in package B. And for the slices 1 and 4 in package B, depending further on the slices in package C. In Chisel, we will identify all those dependencies through the slice definition file in our database, and we will pick all those files necessary and finally merge them into our target file system. A slice definition file will look like in the code box on the right-hand side. Basically, we have some keywords for the slice definition. For example, like package, which is the name of the package that is you normally install with apt. And also essential means the dependencies of the slice. Then its contents means the file to be picked from the package. And for standard slice namings, we have bins, which consists of the executables in this package. And libs is the library, like .so or .a libraries. And data, which is the static data. Config is the editable package configuration files. And finally, copyright. So copyright is being automatically included whenever you chisel any slices in a package. And this satisfies the licensing compliance. And you can also add any slices to the slice definition file if you want, as long as the namings are reasonable. So with Chisel, we can firstly take an example that it can work with Docker file. Now we do in another pattern. We can build from the Ubuntu 22.04, and we can firstly cut the target file system in our host operating system. Then we just do a simple copy from build to rootfs. We can have the resulting file system being copied to an empty image. And on the right-hand side is the real-world example for the same Python 3.11. So basically, we let Chisel cut the files. Say Python 3.11, and the slice name is standard. And we also cut those base files into the file system. And in Docker file, the most important one is we just copy the rootfs to the final, to the root path of the final image, and also properly set the entry point. This results in the image size of only 16 megabytes, and we're still keeping all the core features of Python there, without any distribution utilities that you are going to find in an image that is built from the full base. Then how do we use Chisel with Rockcraft? Still, the changes only consist of 2 lines of code. We only need to give the slice name, which is being separated like with the package name using a underscore. So now, instead of base files, we put base files release info. And instead of normal Python, we put Python 3.11. So previously we used standard, now we use core, so we can further minimize the size of the image. And as long as you put such kind of slice names here, Chisel will be invoked automatically by Rockcraft during the building. And also the Pebble will serve as the only entry point of the image. So this is a comparison of how we build images with Rockcraft. The leftmost one is just the normal one that we build the same as what we're having nowadays in most of the Docker files. And the second one is how we build a distroless image with Rockcraft, but without chiseling its size further down. And the third one is using Chisel. So we have significantly reduced the size of image, and we only include the necessary bits and dependencies of Python 3.11. And the final resulting size is only 14 megabytes. With that, we've also greatly reduced the containing CVEs in this image, because we're excluding the files that are potentially containing CVEs. And we have our image also being tested, that is STIG and CIS compliant off the shelf. Whenever you have the image from Chisel Rockcraft, it's automatically compliant. And here's a live demo as how we can do it. So basically, in the first pane, we are building the normal one, and in the middle pane, we are building distroless, and in the third pane, we are building the chiseled one. And building with cache only costs around 30 or 40 seconds to build such kind of Python runtime image. So we will just do a quick LS to check the size of the image. And you can see the first one is around 42 megabytes. And we copied this OCI archive into the Docker daemon. We just quickly run it to see if it works. Since our entry point is being already set to Python 3.11, but here I use the feature of Pebble. So basically, I type exe, which passes into Pebble, and Pebble will run the second argument with Python 3.11. So yes, for the first one, Python 3.11 is running, and we do the same for the second one. So from here, we can check the built image size is only 29 megabytes. Yeah, and we still run it. It's running. And third one, only 14 megabytes. We still do the same. Python 3 is also running. So with these building recipes, we can easily reduce the size of image, and they still have the same functionalities. So with this such kind of dedicated container for a lean experience, we can have the image size greatly reduced. For example, from the normal Ubuntu, that is in a Docker daemon, it usually goes up to more than 78 megabytes. And Google distroless, yes, they are small. Also the UBI micro. And what we have, the Chisel Ubuntu, is just less than 20 megabytes. So finally, if you are interested, you can join the ROX community and through the matrix and also our discourse. And here are the GitHub repos for the tools that I've introduced during this session. And you can try out just right now. We are all open source. And finally, if you want to follow up and get some like further Q&A, you can also follow up with me on LinkedIn. So thank you very much for listening to this talk.